Welcome to Lesson 3 in the Enhanced Electric Power Quality and Reliability series. This lesson will concentrate on instrumentation. We're going to start by talking about the fundamental concepts used to link instrumentation into computer systems, how computer systems that are digital based are able to link to actual analog processes in the real world and take readings. And then a little later we'll go on and talk about some of the actual instrumentation that'll be put on electric grids. So let's go ahead and start. Just to recap our last lesson, we talked about telemetry. So in the telemetry lesson we talked about the concept of the smart grid required that we make these measurements at a distance, which we call telemetry, and we talked about some of the different measurements that you might want to take in an electric grid, and certainly direct electrical based measurements make a lot of sense. So we're going to be measuring voltages and current flows and power consumed. We're going to be measuring things like frequency and phase angle, and then there are other things that we might not think about as being directly related to electricity, but a good example would be temperature, where we might want to measure and monitor the temperature of a transformer that was in the electric grid, because that might give us an indication of whether or not the transformer was overloaded. If it started to get too hot, we would know that we needed to do something. So not only are we going to be taking measurements in our systems that we would directly think about being related to electric grid operation, but also probably a lot of other measurements that are related to the health of the equipment. So when we start to think about these kind of things, I hope maybe when I was talking about telemetry and measurement that maybe you were starting to think a little bit about, well, how do I connect all these things? How do computers read these things? And the basic fundamental process is analog to digital conversion. So in this little slide right here, you can see I've got some kind of an analog signal, right? So it's a continuous signal. It goes into an analog to digital converter, and then it's converted into bits. It's converted into digital numbers here, right? So fundamentally, this is what's happening whenever there's some sort of measurement being taken. There's got to be equipment in the computer somewhere that allows it to take a signal from the real world and then turn that into bits and bytes that we then put on our network and transport around to gather our information. So when you look at the signal that comes out, of course you've got so for this one, in-bit digital world, right? So arbitrary number of bits, but we got bit 0, 1, 2 on up, and then right here you can see it shows bit 0, bit 1, bit 2, and the digital numbers that come out. So given an analog input right here, we get a digital output right here. Okay, so one of the things you're going to notice here, of course, is that this signal right here can vary infinitely, right, through its range. So let's say we're measuring 0 to 120 volts. We could measure the actual signal, the actual value could be an infinite number of values between 0 and 120. But once we go into the digital world, we're limited in the number of numbers that we can represent in our range. Okay, so this leads to a small amount of error in the measurement. So when we measure this signal, we go from the real value, a floating point value, we come over here to a digital value, and we know that there's a small error associated with our digitizing that signal. And so we have to be aware of that, and we have to deal with that. So analog to digital conversion, and I was trying to think of some examples. Where do you run into this in the real world? And obviously the most obvious example of this is music. Whether you're listening to music from a CD or an MP3, that that music signal, the signal from a microphone, an analog microphone, has been digitized, gone from an analog to a digital number. It's been stored in a computer system, and then in the case of music, it goes through a digital to analog conversion so that it can drive a speaker. And so this right here shows you the signal going into the microphone is continuous. The signal coming out is digitized, so there's a little bit of an error in there. So certainly you've heard the effects of this when you listen to, say, an MP3, where you might have an MP3 that's been compressed a lot, and it doesn't sound quite as good as the original signal because you've lost some of the information. In the case of an MP3, some of that loss of information comes from the compressing and not directly from the analog to digital conversion process, but the idea is there. So when we start talking about storing digital numbers, we have to talk about the resolution of the number, okay? So obviously the higher the resolution, the more closely the output is going to approximate the input. So let's see. So for resolution, a lot of times when you talk about analog to digital converters, one of the primary characteristics of an analog to digital converter, one of the primary specifications will be the bits. Okay, so you can get a 8-bit A to D converter, you can get a 16-bit A to D converter, you can get a 20-bit A to D converter. So what does that mean? Well, let's say I started out, you don't really ever see these because a 4-bit A to D converter would be kind of ridiculous. But if I had a 4-bit A to D converter, 2 to the 4th power over here is 16. So for whatever I put in here, I would only have the possibility of generating 16 discrete numbers. Okay, so I would get this step effect. If I had an 8-bit converter, I can get 256 steps, so I'm getting a little more accurate, right? At 16 bits, I'm actually able to get pretty accurate with 16 bits because I can have 65,536 levels. And then at 20 bits, it's pretty common to see 20 and 24 and 32-bit A to D converters. 20 seems to be pretty common. You're getting 1,048,576 little steps in here. Okay, so when you choose your analog to digital converter, or if you buy in the case of industrial control systems, a lot of times you just buy an analog input card for a computer, and you'll choose a 20-bit resolution input card. So most of the time you'll get the card for the computer, and you'll see and you'll know what the bit level is. So I want to talk a little bit though about the concept of quantization error. Okay, so in this example right here, what's happening is I've got a signal that's coming in. Okay, let's say this is the signal, and I'll do my little thing, and this is time, and this is volts. Okay. And so for this one, I'm going to say this goes from 0 to 1 volt. So my signal comes in and it varies. And over the course of this, I'm going to digitize this signal. So at discrete intervals, I'm going to take readings. Okay. And whatever the value is there, I'm going to generate a table of digital numbers that are going to come out. Okay. So I've got 1, 2, 3, 4, 5 readings here. So I'd have reading 1, 2, 3, 4, and 5. So just to guesstimate here, we would say reading 1 would be 0.5 volts. And let's say this is maybe 0.4 volts and 0.3 volts and 0.6 volts and back down to 0.3 volts. Okay? So each one of these would then equal a digital number. And those would be my readings. Okay, so let's go to the case of half a volt here. So if I go half a volt and I look, that's going to generate my number right here of 011. Okay, but you can see that here between the way the scale's here it's not necessarily, it would have been nice if they had just been by 0.1, but so you can see right here at 0.5 I'm falling directly on this line right here, right? But let's say I'd read 0.45 or 0.4, let's say that's right here, I'm also going to get the exact same number, right? So 0.11. So I've lost my ability really between this many volts and that many volts right here, right? I've lost my ability now to tell the difference between those numbers. So this input is going to produce the same output. So my readings coming out of the converter would probably look more like, say, this. Okay, so this is the results of quantization error, and as you can see, depending on how varied that step is, that's going to determine my amount of quantization error. So the more bits I choose, the more finely grained this is. You know, if I made it more finely grained like that, the better my ability to retrieve the number more accurately. Okay, so this is what we're talking about when we talk about the resolution of an analog to digital converter, the number of bits that it can output, and the result of that, of the number of bits that you can put in, is the number of steps that you can have in your process, or the number of steps you have in your little chart here, and then the difference in the output signal that you generate. So quantization error, obviously you want, you know, as many bits as you can get reasonably out of your analog to digital converter, and that's how your signal is going to look there. So again, quantization error just relates to the fact that between yeah, hold on, my pen's not behaving here. Okay, so quantization error just is the fact that I blew this up a little bit so you can see it a little better, that between this voltage right here and this voltage right here, I get the same output of 0.10. Okay, so if I'm taking readings that look like, you know, that fall along here, they all generate the same output. So the lower the resolution, the lower my ability to, or the more likely I am to lose some of my resolution in my readings.